This is a recap of Module 6 Lecture Part 2 and Module 7 Part 1. If you would, turn in your notes to the last page, not of 5. We talked about molecular and empirical formula last week when we finished up. Let me reread those and go over your terms just to remind you. We had to hustle through that stuff, sadly. So the molecular formula is a chemical formula that provides the number of each type of atom in a molecule. And we introduced that some time ago. But then the empirical formula is a chemical formula that tells you a simple whole number ratio for the atoms in that molecule. So in other words, it breaks down a molecular formula to its smallest, least common multiple. How about that? Me and my math terms. In your notes on page 2 for Module 6, they say to go from a molecular formula to an empirical formula, find the common factor and divide by it. All right, so common factor is actually the term. And we'll look at a couple of examples. And then to go from an empirical formula to a molecular formula, find the common factor and multiply by it. So it's just that simple. The common factor is the mass of the molecule divided by the mass of the empirical formula. So the division there is fairly simple. Again, it's the common factor. Least common multiple, I guess, is another way to explain it. We looked at the examples on page 6.9 last week to determine if it was an empirical formula. And so we had, you notice C4H12, and there is a common factor that will divide into C4H12, and it is 4. So you would end up with CH3 in terms of going from the molecular formula to the empirical formula. Same thing with Na2S2O8. The common factor is 2, and you divide all of them by 2. But if you'll notice the last K2Cr2O7, there is no common factor for any of those. So in this instance, the molecular formula is the empirical formula. On the next page, there's a few examples too. Compounds, I'm looking at example 6.10 on page 187. A compound's empirical formula is determined by experiment to be CH2O. In a separate experiment, this molecule's mass was determined to be 180.1 AMUs. And so in this instance, what you're going to do is look up this particular formula. They want to know if what the compound's molecular formula is. And so in terms of this thing, the mass was determined to be 180.1 AMUs. Well, let's add up the mass of the molecule that we're given, CH2O. Well, I can tell you right off, there's no way that that's going to be 180.1. And so there is the way that they do it. One carbon atom is 12. How do we find that? Again, from your periodic table. It's the numbers right below the molecular symbol, the elements symbol. And so, of course, you've got 2 hydrogens at 1.01 and 1 oxygen at 16. Well, those add up to be 30. Well, so how are we going to figure this? What would be then the actual molecular formula of this thing if, as it turns out, the molecule's mass is 180? Well, what you're going to do is divide what you have in terms of the 180 by what you added up in the actual mass of a CH2O molecule. So in this instance, 180 divided by 30. So your ratio or your factor is 6. So you're going to multiply everything you've got by 6. So you're going to end up with C6H12O6. All right? So again, we're having to hustle, so I want to go do one more example, and then I'll see if you've got any questions about this stuff. Let's look at 6.12 on page 189. A sample of brown colored gas is decomposed into 2.34 grams of nitrogen, 5.34 grams of oxygen. What is the empirical formula of that compound? Well, in terms of the nitrogen and the oxygen, we know that they exist in terms of the decomposition as homonuclear diatomics. So it's N2 and O2, and the mass, by virtue of looking on your periodic table of nitrogen and oxygen, nitrogen number 7 is 14, oxygen number 8 is 16. 2 times both of those things, that's what they're doing there. You see the mass of nitrogen times 2, because it's a homonuclear diatomic, is 28. And so a mole of nitrogen is 28 grams. Remember what we did there in terms of the last couple of modules, converting the atomic weight into moles. In other words, AMUs in grams is the number of grams in a mole of that stuff. So you have then, in terms of what they gave you for the number of grams that was decomposed was 2.34. That was given to you in the problem. You found out how many grams are in 1 mole of N2, and you divide that then, and you end up with 0.0836 moles of nitrogen. You do the same thing in terms of the oxygen. We do the exact same thing, and then turn over to the next page if you would. So in terms of the ratio there, you have 0.0836 moles of nitrogen that you solve for, 0.167 moles of oxygen. So your question in terms of what the molecular formula looks like, it has to do with that particular ratio. You've got 0.836 moles of nitrogen and 0.167 moles of oxygen. Well, in terms of that, to divide the 2 by, to find that common ratio there, you're going to divide the 0.836 by the 0.836, and you're going to add that to the 0.167 divided by the 0.836. And in terms of this thing, you're going to end up with 2 moles of oxygen and 1 mole of nitrogen. And so ultimately the empirical formula then, by breaking that down, is NO2. So again, we went quickly through that. We just about have to in terms of what we're going to do next. The test will feature a little bit of that stuff, but what I really need you to know in terms of this module is what we did earlier. The test is going to feature the movement from, go back to page 179 if you would, the movement from grams to moles to grams. And so that's what I need you to be able to understand and calculate in terms of questions on the test, and especially then for the future, because this is stuff that sadly we're going to have to do for the rest of the course. So, is there questions especially about the stoichiometry? That is the process of going from grams to moles to moles to grams. Got it all. I don't see those hands shooting up. All right. The way it has to work is, if you don't want to ask me in here, if you're struggling with this stuff, please don't let it get away from you. Please, email me or call me. Some of you have done that, and I've been delighted by it, and I will be delighted by it again. If you're struggling with this stuff, just give me a holler or email me, and we'll get it. It's not hard. As I mentioned to you in terms of the stoichiometry, it's just a matter of steps. It's trying to go from one step to the next, and it harks back to our good old factor label method. What we learned in the first module is what we're continuing to build on. Is there any questions? Are you sure? Going once, going twice. All right. Let me take a quick peek at that test one more time, and I'm going to hand them to you. Just a fast update too, and what we're going to finish up with. So of course next week is Thanksgiving, and obviously we won't meet. We'll be back the following week. We will lecture through the second half of Module 7. I will hand you the test for Module 7 to take home, incidentally, plus an extra credit option that doesn't have to do with chemistry. It has to do with my day job. So you may do it if you like, and if you don't, that's okay too. I will hand those to you next week. You know, ordinarily you get the test the week after we lecture through, but the problem is the semester's over. So the following week is our last meeting. So throughout the week then, in terms of the second half of the material, that's what you're usually responsible for, to do the homework for after I lecture through it. Well, you'll just have the test, and you'll do the test before you come back on the following Thursday. So in years past, we've had a little party or something, but I don't know that we're going to do that this time with the crazy COVID stuff. So I might do some lab stuff, but once again, in terms of you guys doing it, I think probably what I'd do is just do it up front here and have you watch. Sadly, this is not a chem lab, and with COVID, everything is compounded. Let's see, anything else? I don't think so. Let's hand out your stuff then. Liam, you should have stuff in your email in terms of test and terms. I've got to get your 6 tests today too, I think, and check your homework. Okie dokie. Or did I just give you 6? I just gave you 6. I know I'll get this together. Turn to page 201. 201. So there's an interesting discussion of the historical overviews of the stuff that we're going to do in terms of atomic structure. And I'm not going to take a long time going into the history of it, just because the history is interesting, but don't test you over the history. What I want you to know is what's in your notes, of course, as always. The history is interesting, especially as this author writes it, because so many, just to remind you, and I do this from time to time, but so many of those scientists upon whose shoulders we stand, modern technology and such, were committed believers. And the idea that science is something that is left to non-believers, that, you know, believers are dabbling in mythology while the real smart people are doing the good stuff in science, is a travesty upon the history of science, and modern science, I might add, as well. But so many of the scientists that came up with the stuff that, again, is the foundation for so much of what we do and know now, understood that God is a rational being, and He creates in a way that is reasonable and deductible. In other words, that you can examine it, and what you find will be true if it's true today and true tomorrow. This is not a random hopscotch world. It's a world put together piece by piece, and it makes sense. And so we can explore, we can look deeply into subjects and discover because of who God is and the way that He reflects who He is in His creation. So, with that said, turn over to page 203 in your notes. This is the beginning, of course, of the discussion on electrical charge. And as I say, what I want you to know is in your notes, and so let's just go with it. There are 2 types of electrical charge, which, of course, most of you know, positive and negative. That which does not have any overall electrical charge is considered to be electrically neutral. So you have positive, negative, and then neutral. And we'll look at at what it means to be neutral in just a little bit. It's not that something does not have electrical charge. It simply is that the charge that it possesses cancels itself such that it's neutral. Like charges repel one another. If you've ever messed around with magnets of any kind, you found that. So you try to put it together and they repel one another. Opposite charges attract. And so that's the case with, again, with the use of magnets. That's what you've noticed anyway. And so this is the statement that I just told you. Every substance on earth has an electrical charge. However, if there are as many positive charges as there are negative charges, the substance has no charge overall. So if in itself it has -1 and a +1, then it's going to be electrically neutral. They cancel one another. If there's more than one charge than the other, then the substance will take on the electrical charge of what is most. And again, in terms of the illustration there, so if you have a -2 and a +1, you're going to be -1 and be slightly negative in charge. So turn over, if you would, in terms of, again, there's great discussion of Crook and Thomson and Dalton in terms of their understandings of things, and in terms of their theories on things, and they really are interesting. But for our sake of time, we won't go into that history. The definition of electron, I've filled it in for you this time. Electron is one of 3 particles that make up the atom. It is negatively charged and orbits the nucleus of the atom. So I'm certain in your first biology courses that you were introduced to the basic components of the atom, and that's one. It is the electron, and it orbits the nucleus in some respects in interesting ways, and we will discuss that and look at those orbits in the second half of this module. Some neat stuff in this module. You know, I give you my opinion about stuff I like and stuff I don't. And this module is kind of cool. I like this stuff. So that's an electron. A proton is one of 3 particles that make up the atom as well. It's positively charged, but it is in the nucleus. It does not orbit this thing. And then finally, the neutron is one. Well, it's the 3rd, perhaps, of the 3 particles that make up the atom. It's electrically neutral, and it too exists in the nucleus of the atom. So, here we go. Get your periodic tables out again. We've got more information to discover about the periodic table. We've learned all kinds of stuff, haven't we? We've discovered in terms of of course, the naming of these various elements. We discovered how that was done in terms of the first letter of the element in the English or the Latin, and then sometimes the second letter as well. We found out about why the atoms exist, the elements exist in the order that they do, and that's based on the mass of the atom. You notice hydrogen is 1.01 and helium is 4, lithium is 6.94, beryllium is 9.01. So what we have is an ascending mass of each one of these elements. In just a moment, we're going to find out why that is in terms of these elements. And then the other thing we learned was vital, and as I've mentioned to you, it's what you learned in the last couple of modules, crucial to the rest of the course, and that is the fact that in terms of the atomic mass in AMUs, if that same number is determined to be grams, that means that that's the number of grams that 1 mole of those atoms weighs. That's the mass of it. So 6.02 times 10 to the 23rd atoms of helium weigh 4 grams. All right. So we've discovered these neat things about the periodic table. Well, here comes another one. As it turns out, and again, I'm reading from your notes, an atom's atomic number tells you how many protons and electrons it contains. Now that's pretty stunning. And I might add, very important information in terms of our understanding of atoms. So we noticed, and we just made the point, that the mass of these things go up. They ascend with each number, each atomic number. Well, now we know why. There's more electrons and protons in each one of the elements as we ascend. All right? So there's, in terms of, let's just do helium. In terms of helium, there are 2 protons and 2 electrons. All right? In terms of lithium, there's 3 protons and 3 electrons, and so on and on we go. All right? And all atoms have an equal number of electrons and protons. All right? So we're going to find out about neutrons here in a little while, but that's 2 important statements. So all atoms in their natural form have the same number of electrons and the same number of protons. All right? I think I'll just stop there for a second and see if you've got any questions about that stuff. All right, it's just basic information. It's structure, but in terms of it, it's important. So turn over to page 206. So I want to define an isotope. So an isotope are atoms with the same number of protons, but different numbers of neutrons. Yeah, you can actually have that. So we just made the statement that all atoms have and again, in their natural state, have the same number of electrons and the same number of protons. And often they have the same number of neutrons, but not always. And when they don't, there's a word for that, and it's called isotopes. All right? So it is a form of that element, but it's a little bit different. Look at the next statement in your notes. Isotopes behave identically in their chemistry. The main difference between them is in their mass. And that makes sense, right? Because if you're missing a neutron, or if you've added a neutron, it's either going to be less or more, right, in terms of its mass. Not a whole lot, but a little bit. So the main difference is in the mass of that thing. Other than that, the characteristics of isotopes are for the most part identical. Okay? Again, important, fascinating information in terms of this thing. Now, mass number. I didn't define this for you, so would you please write this down in your notes? It's there right on page 207. Mass number is the total number of neutrons and protons in an atom. All right? So if you add the protons together with the neutrons, you get something called mass number. All right? Now, if an atom, a particular element, has isotopes, you will have isotopes with different mass numbers, right? Because you have a differing number of neutrons that you've added to the protons, and you come up with a different number. All right? Turn over to the next page in terms of isotopes and nuclear bombs. Let's see. Yeah, we need to get a little further here today. All right, and we will. But that means I'm not going to go into a lot of detail about nuclear bombs this morning. Anybody here making one right now? Anybody? Okay. Would you let me know when you get that done? In terms of it, you know, that's the big issue in international politics, and it will be in your lifetime. More and more nations are achieving the technological prowess to be able to do this, to enrich isotopes in order to make nuclear bombs. Isotopic enrichment, I have the statement of it down at the bottom of page 1 of your notes. The process by which an abundance of one isotope in an element is increased. This typically is used in order to make fuel for nuclear bombs. All right? So the discussion of that is there on page 208 and 209, and it is an interesting discussion in terms of the naturally occurring isotope that's necessary to be used in terms of, again, making a nuclear bomb, an isotope of uranium. It does not exist in very much quantity in nature. And so what has to happen is a chemical process by which you form those isotopes. And for the longest time, that was the trick. And that was what kept Hitler and Mussolini and others in World War II from achieving success in building a nuclear bomb. And if they had, Hirohito and Japan, if they would have, they surely would have used them all over the world. Evil is just that way. But in any respects, now many nations have either stolen or developed that technology and are able to do that. North Korea is the latest. Iran, there's lots of efforts to try to prevent them. I don't know how ultimately that's going to work out, simply because the technology is what the technology is, and so in your lifetime, sadly, and I think, you know, the United States has been very interested in developing means by which to defend against these things. You know, that sadly in a fallen world, you know, defensive measures are met by new developments in offensive measures, and on you go. But you just got to pray about that stuff, y'all. I don't know what else the answer is other than continuing to develop those defensive means. But the discussion on how it's done is interesting. We're just not going to take a lot of time. So look at, turn over to the next page. Well, no. Stay on the atomic model in more detail on page 209. So a model, again, I've defined it for you at the bottom of page 1, is a constructed image of something that cannot be seen with our eyes. At least that's how we're defining it in chemistry. So how does something work? What does it look like? And so scientists have devised models and then tested against those models to see if their model is accurate. The plum pudding model, it was one in the beginning in terms of where electrons would be, and then the positively charged pudding in terms of what that might actually do and work out with in terms of reality. And so this plum pudding model, I wanted you to look at it just as an example of something that was in terms of scientific testing was determined to be inaccurate. The Rutherford model is discussed here, and how he did the experimentation. And again, I'm just going to have to leave it with you. But turn over to page 2 of your notes. The Rutherford planetary model is a model that said the atom is made of a dense, positively charged nucleus with electrons orbiting the nucleus in circles. And in terms of Rutherford's experimentation, he was sharp as a tack, and so in terms of how that works out, it turns out to be true. And we're going to find that then other scientists have built on Rutherford, and we'll discuss that in this module. So we're continuing, though, to simply define some things. In your notes, page 2, the nucleus is the center of the atom that contains the the neutrons and the protons. So that's what Rutherford determined in terms of what the structure of this thing looks like in general. The planetary model, again on page 211, meaning the nucleus is orbiting the electron is orbiting the nucleus, not unlike satellites orbit the Earth. The Earth orbits the Sun. But we will discover again that there is some difference in terms of that as well. So and that's in next week's discussion, and it's pretty fun stuff too. Page 212 describes again more of what Rutherford did and how he arrived at his conclusions. We got to introduce light, though, and then I think we'll be okay, and next week we'll be able to finish up and not be harried about this stuff. If any of it is confusing to you in terms of what we just said, again, the background for it, please read your textbook. It's an interesting read anyway. I mean, it just is. This guy writes in a way that doesn't put me to sleep, and if it, believe me, if it doesn't put me to sleep, it won't put you to sleep. If you haven't found that already. So turn over, if you would, to page 213 in terms of the nature of light. Again, we're going to define some things and then discuss it. So no one knows with absolute certainty what light is, or we can describe it in some ways, and that's what we will do here. Is light is it particles? Is it photons? That's what a photon is. Is it a photon in terms of a particle in and of itself? But light also acts like a wave, and we'll look at what that means in just a second as well. And it does both. And so the question is, how can it be both? How can it be both a particle and a wave at the same time? And so when you don't understand something sometimes, if something has attributes of two different things, well, let's combine them, and that's what they've done. They have created the particle-wave duality theory, and that sort of describes it in and of itself, doesn't it? It simply says the theory that light sometimes behaves as a particle, and sometimes it behaves as a wave, all right? And that's just the way it is. It's a mystery. It's, you know, I like to tell folks in terms of teaching the scriptures that there's much in the scripture that's a mystery as well. There's much that seems to contradict, and we wonder how something can be something at the same time and yet be different. The Trinity, for example. One God in three persons. How is that possible? Well, you know, in terms of our finiteness, we can't comprehend that. The Latin term for that is finitum non compax infinitum. It simply means the finite can't comprehend in all of its depth the infinite. And that's the case too in some instances of science. We don't understand about light. So what we do is simply punt and say both things are true. We observe them both to be true, and they are. So particle-wave duality. If you would, turn over one more time to page 214. So light behaves like a wave. It does. And what's a wave? Well, there's a picture of a wave. And you know what a wave looks like. There's your wave. Right here. If you've been to a beach anywhere in the world, and any kind of a beach, I suppose, even lakes in some respects, you've seen waves. You surfed waves. You've body surfed waves, and so you will understand these terms by virtue of your experience with waves somewhere in your bathtub. You've experienced waves in your pool. You've experienced waves. Some big guy jumps off the diving board, right? So wavelength is the distance between the crests or the trough of a wave. Incidentally, there's something nice for you to draw in your notes, all right? Great little depiction of what it means in terms of these terms about light. So the distance between crests or waves, that's a wavelength, all right? And it is indicated by lambda in terms of the Greek alphabet. Amplitude is a measure of the height of the crests or the depth of the troughs of a wave. And so look at amplitude. There you go. In terms of the beginning of that particular wave on 7.7, the amplitude of it is A. And yet, if you go just a little bit further in terms of this wave, you see that the amplitude is much larger. All right, the further the wave goes. So the amplitude certainly can change, as well as the wavelength, depending on the energy. The visible spectrum is the range of light of wavelengths between 700 nanometers, that's red, and 400 nanometers, that's violet. Look over on page 213. And you get a picture of that too. I can't believe the time is up, but we're just going to have to quit here. And we will. I think we're going to be fine in terms of getting the rest of it. Yeah, I think so. So the next stuff, like I say, it's fun too. We will look at the quantum mechanical models of the atom. That's going to add to Rutherford, and I think you'll find that fascinating. But take a good look at the visible spectrum here in terms of it. Roy G. Biv is just a handy-dandy way of remembering the visible spectrum. Roy G. Biv. The acrostic is red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. So easy for me to remember for some reason. In any respect. Well, we're going to quit there.